In this lesson, we're going to continue on from our understanding of our basic understanding of derivatives and gradient functions. And we're going to look at three specific things. We'll look at increasing and decreasing functions. We'll look at sketching derivative functions through extrapolation. And we'll end up looking at calculating angles formed between the x-axis and tangent lines. Okay, so if we start with increasing and decreasing functions, the concept here is pretty straightforward. The idea is that when a function is increasing, so that's a scenario where we've got a function that's going up, then it's going to have a positive gradient, which means for that section, the derivative f dash of x will be greater than 0. Okay, so when it has a positive gradient, when it's increasing, then the derivative must be greater than 0. And conversely, that means that when a function is decreasing, so we can see here that a function going down will mean that it's got a negative gradient, and thus the derivative, that gradient function for that section, will be less than 0. So it'll be a negative value. Now finally, when a function is neither decreasing or increasing, it's going to be stationary. And so that means we're looking at something like a turning point. And so we'll be looking at these points here, A and B. Then the gradient in this case will be 0. And therefore the derivative will also be equal to 0. So those are very, very important facts when we're dealing with derivatives and gradients. And so when we're looking at increasing and decreasing functions, that's what our focus is. So when is it increasing? When is it decreasing? When is it stationary? And what does that mean for the derivative? So increasing, decreasing, and equal to 0 respectively. So if we put this into practice, looking at example 14 from the textbook, it asks us a really simple question. It says for the graph y equals f of x, it doesn't define the true function here, but it just says it's f of x. Now, we want to find the values of x for which, in this first one, it's saying the derivative is greater than 0. So what that's asking for is, when is it increasing, or when is that gradient greater than 0? So we should be able to see here that it's increasing in this section here. So between x equals -1 and x equals 5. So I would say this is simply when x is an element between -1 and 5. So pretty straightforward to see that it's increasing and that gradient is positive between -1 and 5. When we look at part B, and it's when the derivative is less than 0, so when it is sloping down, we can see that there's two sections now. We can see that when it's less than -1, and also when it's more than 6. So for both these, we've got a negative gradient, it's sloping down. So we can say when x is an element of, sorry, that's probably not the best way to do it, when x is less than -1, or when x is greater than 6. Now, I probably have made a slight error in the first one as well, because I've included -1 and 5. But what can we see happening at -1 and 5? They're actually stationary points, they're turning points. So here, it would have been better for me to have these circle brackets to say we're not including -1 and 5, but it's all the values between them. When we get to the third one, and we're looking at when the derivative is equal to 0, there's two distinct points. So it's at 5, and it's at -1. So in this case, we'll just say when x is equal to -1, we've got a stationary point, that gradient, that slope is 0. And when x is equal to 5, it's also the same thing. We've got that stationary point. That slope or that gradient is equal to 0. So hopefully that makes sense. It's easy to kind of break it down and go, okay, this is sloping up, down, or it has a gradient of 0. Right. So the second thing that we said we're going to look at is sketching derivative functions, so extrapolating from graphs. So the idea here is pretty similar, but there's a couple of important things that we can carry on from what we just talked about. So let's look at just a random function. So I'm just going to draw a line here. Look, there it is. This line represents f of x. Now the important things that we want to do at the start here is recognize where our stationary points are, because what does that tell us? That tells us that the derivative is equal to 0 here, and the derivative is equal to 0 here. So that means if we're drawing the derivative function, and let's draw that in green, then these 2 points are zeros in the derivative function. Now for the rest of this, it's about recognizing what's happening in these sections. So if we look at our section over here, when we're less than this stationary point, what is it doing? So can we see here that it has a negative gradient? So gradient f dash of x is less than 0 in this whole section. So that means if we're drawing that gradient function, in this section down here, it's going to be negative values. So we can draw in that. Now, when we then look at this next section, we can see that it has 0 and positive and 0. Now, if we look really carefully, we can see a change in concavity here. Now, we don't have to know too much about this at this stage, but what this is saying that there has to be a point where that slope starts decreasing again. So it's increasing, 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 and it starts decreasing and goes back down to 0. So in this whole section, we know that the gradient is greater than 0. So it goes up and then back down. And then finally, when we look at this last section, again we have a decreasing gradient. So f dash of x is less than 0 again. So we end up with our gradient being negative in this last section. Now, if I was truly doing this first section right, I probably would have drawn it to look more like that. All right. So hopefully this makes sense. The big parts of this process is about working out, okay, where are the stationary points? And those stationary points will end up tracking to be zeros. And in which sections are we positive and negative. And then we can always draw a rough sketch of what that derivative function will look like. So if we look at these 3 examples here, we'll try to draw on top of them what the gradient functions look like. So we know here we've got a stationary point. So straight away, this stationary point means we've got a 0. On this left-hand side, we have a negative gradient. So f dash of x is less than 0. And over here, we've got a positive gradient. F dash of x is greater than 0. So really, it's just a matter of realizing that we've got a negative gradient, a positive gradient, and we end up with a straight line function in this case. When we look at the second one, hopefully we can see that this is just a linear function. And because we've got these 2 points here, we can work out the gradient being rise over run, which is 1 on 1 So the gradient is 1. At every point along here, the gradient is the same, correct? So we should be able to go, well, the graph of the gradient function in this case is always 1. So this is our f dash of x. This was our f dash of x in the first one. Right, so now when we look at the next one, it's a little bit more complex, isn't it? Here's our stationary point, and here's another stationary point. Here, in this section, we're looking at a positive gradient, so f dash of x is greater than 0. Here we've got a negative, and we have that concavity change somewhere around the middle. So this is f dash of x is less than 0, and then we've got an f dash of x is greater than 0. It's going up, back up again. So if we're going to draw this, we've got our 2 zeros. In this middle section it's negative, and in the 2 edge sections it's positive. So there is our gradient function. Now they don't have to be perfect, but they just have to represent basically what's going on, so we can get an idea of what the gradient would be doing throughout these functions. Okay, so the third thing that we're looking at is calculating angles formed between the x-axis and tangent lines. So the idea is pretty straightforward. If we take any function, so let's just draw our f of x up here, and we find the tangent of that function at any point. So let's say at this point here, we can draw in our tangent. That tangent line will always cross the x-axis. And when it crosses the x-axis, we can look at this angle that is formed. Now, really what we're looking at is a scenario here where we have a change in y and a change in x. And I'm hoping that you know that a change in y is just a rise, change in x is a run, and because we know our trigonometry, we can say that tan of that angle will be that rise over run. Now, rise over run is simply a gradient, and that gives us the rule that we're going to work with. We're going to say that tan of the angle will always be equal to the gradient. And the cool thing for us is that we already know that the gradient can be determined by looking at the derivative. Okay? So as long as we can work out the gradient, or we know the gradient of that tangent line, we can always find the angle between the axes. So let's have a quick look at an example so we can put this into practice. Now it all comes down to this tan theta is equal to m, which is the gradient, and our derivative processes that we already know. Okay, so first one says find the coordinates of the points on the curve with the equation. So we've got the equation y is equal to x squared takes 7x plus 8, at which the tangent line makes an angle of 45 degrees with the positive direction of the x-axis. Alright, so we'll start with this. The angle is 45 degrees from that tangent line. If we drew this out, it would look something like this, obviously passing through 8. And what we're trying to find is that tangent that makes an angle of 45 degrees with the positive direction of the x-axis. So that means we're looking at finding this coordinate x, y, so that we get this nice 45 degrees here. Alright, well the first thing we can work out is the gradient, because we know that m is equal to tan of the angle. So m, or the gradient, will be equal to tan of 45. Now we should know that tan 45 is equal to 1, so the gradient will be equal to 1. Alright, so that's number one. That's pretty important. We know the gradient will be equal to 1, so that also tells us that the derivative will be equal to 1. So next thing we need is a derivative. So we practiced this last lesson. Derivative of x squared is 2x. Derivative of negative 7x is negative 7, and the derivative of 8 is 0. So we want to find what x is when the gradient is 1 or the derivative is equal to 1. So 1 is equal to 2x takes 7. 8 is equal to 2x, and therefore x is equal to 4. Now that we've got the x value, we need the y. So if we go back to the original, and we say, well, x is equal to 4, so y is equal to 4 squared takes 7 times 4 plus 8. We've got 16. Take away 28 plus 8, and we end up with negative 4. So the answer is, the coordinates are 4, negative 4. So at that point, the derivative, or the tangent that's created from that derivative, creates an angle of 45 degrees with the x-axis. Okay, so pretty tricky. This is a complex familiar type question. Now the second one's a little bit easier. It says find the coordinates or the points of the curve with the equation blah blah blah, at which the tangent line is parallel to the line y equals negative 2x plus 6. Now the equation's the same, so we know that our actual equation f of x is equal to x squared take 7x plus 8. It will look the same, but we're asking, when is that tangent parallel to this? Now the big thing is, what are we talking about? What's important when we're parallel? And hopefully you can recall that when we're talking about parallel, then the gradient will be equal. So that means that we're saying that the gradient will be equal to negative 2. Which means that the derivative must also be equal to negative 2, because the derivative is used to find that gradient. So we're trying to do the same thing again. Instead of m being equal to 1, like the last time, m is negative 2. So the derivative is 2x takes 7. That hasn't changed. It must be equal to negative 2, and we're trying to find the x value of where that occurs. So we add 7, and we end up with 5 is equal to 2x. 5 by 2, and we get x is equal to 2.5. Now if we put that back into the original, we've got f of 2.5 is equal to 2.5 squared. Take 7 by 2.5 plus 8. That'll be 6.25. Subtract 17.5 plus 8. Means we've got 14.25, subtract 17.5, and we end up with 3.25 negative. And so that means our point is 2.5 and negative 3.25. So I'm hoping that you can see the idea here, and it's probably a little bit more complex. In each of these questions, you'll have to think about it a little bit more. But in each of these scenarios, they gave us information that would allow us to determine what the gradient is. Working backwards from the gradient, we were able to apply that to the derivative and work out what the coordinate was that would fit the scenario. Okay, so that concludes the lesson. 3 different techniques, but with similar concepts behind them. Okay, thank you.